So this is our electromagnetism, our unit number 7 final exam review. This chapter was just packed full of various things, so it's a bit tight trying to get all the theory down onto one page, but here it goes. We started off taking a look at permanent magnets and magnetic field lines, and so on the right there, that little square, I'm just going to turn that thing into a magnet, and let's say that this is the south end and this is the north end. And one of the things that we talked about at the very beginning was how magnetic field lines, they come out of the north end. So let's say they go from north to south. So they're going to come out of the north end of this magnet. I'm going to go like this. There's my B field coming out of this thing. And they kind of come out and then turn, right? And they kind of double back towards the back end of this magnet. And then they're going to be going and diving into the south end of this magnet. And a compass, which is what I'm going to use these little circles to represent, a compass is great because it actually points in the direction of the magnetic field. So that's what a compass is good for. It's a little magnetic field direction indicator. So those little compi would point that way. Then we talked about how you could use electric circuits, or electric currents, maybe I should say, to generate magnetic fields. And the first situation was the long straight wire that has magnetic field circling around. You have to do that right-hand fist grab in order to figure out which way it's going to go. Another way to draw this, if you're not good at drawing the 2D or 3D picture, is you can draw it on your 2D paper by putting dots over here where the magnetic field is coming out, and then putting X's over here where the magnetic field is going back in. And the R talks about how far you are away from the wire. Because as you get farther away with this R down here in the bottom, that value for B drops off. A much better way to create magnetic fields is to actually use a solenoid, an electromagnet. It produces a nice steady magnetic field. Just a little thing to point out, in this equation there is no diameter. It does not affect the value for the magnetic field at all. Just the length does. We've got these two different versions of this equation. They're really the same thing. This part here, you have to go and calculate the coils per meter, and sometimes people go and do that calculation for you. That little n is actually coils per meter. Be careful on trick questions where they might actually give you little n. They might give you coils per meter, and they might tell you how many meters long it is. Don't divide, right? If they give you coils per meter, just go with that little n version, and you're all good to go. We don't like to do this long straight wire one very much because it doesn't produce very strong magnetic fields. The solenoid is better, but you still need that long straight wire fist grab in order to figure out which way the B field goes on the inside. So to do that, I always imagine maybe taking this wire right there, that wire that's in red, and say, okay, why don't I go and do one of those fist grabs? I'm going to grab it right here to try to figure out which way the B field is going on the inside. Once you've got some magnetic field, either from permanent magnets or from electric circuits, then you can actually start producing some forces on charges that are moving. And if you've got just a single charge, like a proton or an electron flying through a room of B field, then you can go with QV crossed with B. It is a cross product, so be aware of that. If the velocity is there, but it's not crossing the B field, if there's no cross, there's no force. There has to be a bit of a crossing of the B field. But this deal with the right-hand rule, with your thumb being the velocity, then you've got that you be good finger and then the F finger there and for your middle finger. This is great for stories with, protons flying through a room, or maybe electrons flying around through a room. But oh man, be careful with those electrons. They're negative, so they're going to disobey that right-hand rule. You're going to have to switch your answer around. Another thing we talked about for charges that are moving in a magnetic field is just kind of the path that they follow. We call this cyclotron motion because it's like what they do down at Triumph. In that situation, if you look at F equals ma, you end up with QVB for your force, and that's equal to the mass times that circular acceleration. And most physicists like to cancel one of the V's and move the R, and the most common arrangement to use here is QBR is equal to, well, it's the momentum, mv. If instead of a single proton or a single electron, if you've got some charge moving along a wire. You've got some electric current. Then we just modify things a little bit. We're going to modify the right-hand rule. This won't be velocity anymore. We're going to change that out. We're going to say, oh, our thumb will be I. It's still a cross product. So if there's no cross, if that current is happening but it's not crossing the B field, if there's no cross, then there's no force. And we're just going to use good old traditional Benjamin Franklin current direction. We're not going to worry about electrons moving in wires. We're just going to say, which way does the I go? For the second half of the chapter, we looked at how you could actually generate voltage. We looked at Faraday's law of induction over here on the left. We've got Lenz's law. That's this negative sign. That talks about which way that current's actually going to be flowing, trying to stop you from making those changes in magnetic field. And in order to calculate this voltage with Faraday's law of induction, we need to know that flux, measured in Webers, is actually magnetic field in Tesla multiplied by the area of the opening. And so if you're trying to figure out, according to this deal here, changes in flux, then changes in flux will be the final flux minus the initial flux. That's how we always measure change. And I can tell you that very, very often, it's actually the B field that's changing. So very, very often, this change in flux is going to be the change in the B field multiplied by the A. We rarely change the A. It can be done, but we rarely do it. Another way that you can generate voltage, it's actually the same thing, but this is just a convenient rearrangement for the equation, is the wire that's crossing across B field. It's cutting across the B field, and that's where you get that BLV. Be a little careful here. You got to ask yourself, is all of this wire actually cutting across the B field? It might be a very long wire, but maybe not all of it is actually cutting across the B field. So I'm just going to leave a little note here. Got to ask yourself the question, is all of that wire crossing the B? Well, let's say crossing the B field. Only the section crossing the B field should be counted in that equation for the length of the wire. Last couple of things. For motors, when motors are running, that rotating coil does behave like a generator. It has a BLV action to it. So it's going to create a voltage, and it's actually a voltage that fights the source voltage. So we had, in purple there, we had that rearrangement of Ohm's law with that effective voltage up in the top. And that back EMF is proportional to speed. So if you're working with a drill and the drill hits some tough material and slows down, then that back EMF, well, it's going to drop if it slows down. So I'm just going to write that down here. The back EMF drops, it reduces, if the motor slows down. Take that to the extreme. The back EMF will be 0 if the motor is stopped. So I'm going to say it's equal to 0 at startup, when you first turn the motor on, or in what we call stall condition. If you take your drill and it's hit such a hard piece of material it actually stops, but the motor's trying to run, then you're going to run into a situation where the back EMF is 0. For transformers, the crazy little red arrows here, that was just what we talked about in class about how the voltage is nice because it's proportional to the number of turns, but the current is reversed. Because of conservation of energy, conservation of power, the currents don't follow the same pattern exactly. A couple of things to point out, little bits of theory. If people talk about whether a transformer is step up or step down, a step up transformer, well, that's going to cause the voltage to increase. Okay, just putting it in simple terms, the voltage increases. You want to get kind of technical, you could say, oh, okay, the secondary voltage is better than the primary voltage. Sure, another way to say the same thing. Couple of last little issues with transformers. Because of the idea of conservation of energy, you're going to find that the power in is equal to the power out. You can't create power. Now this is assuming your transformer is 100% efficient and it doesn't generate any heat. That's all we ever do for Physics 12. So we can say power in equals power out. And one last thing, we saw that you can still use Ohm's law, perhaps on the output side of your transformer. You can say the current in the secondary side it's going to equal the voltage in the secondary side divided by the resistance of whatever the thing is. We had a little toy in our example in Physics 12, so it's like the resistance of the toy. So you can still do Ohm's law sometimes to get somewhere with current over on the output side of the transformer. All right, crazy amount of theory. Let's try a few questions out. So these are just pirated off of old provincial exams. This one here, in which diagram would the current carrying conductor experience a magnetic force out of the page? All right, I wanted to put this one on here just to point this out. I want to point out what this question is not talking about. This is not a story about the B field created by a wire with current in it. So if I've got a wire and it's got some current flowing like this, then that thing actually generates a magnetic field, and that magnetic field will circle around it, and I can use my right hand rule where you grab it like a fist grab with your right hand and see that the B field does this. And some people might draw that as dots over here and X's over here. This question is not talking about that. Okay, so we're not talking about the B field going around a wire. But as soon as you see these pictures, sometimes we kind of get trapped into thinking, oh yeah, it's about that. No, this is about the force on a wire. This is all about LIB. Okay, so let's kind of get into that mindset where we're going to say, yeah, there's this force because we've got this length of wire with a current in it crossed against a magnetic field. And so the only one that's right, if you use your right hand, if you play around with these, it's actually D. Your thumb on your right hand has to point this way. Okay, so there's the I. It's going to be your thumb goes here. And then your next finger, your index finger in your right hand has to point down. That's this one here. And you'll find that the force, the F finger, the middle finger in your hand is coming out of the page. And D is the only one that does that. 25. Okay, I've kind of picked all these questions for very deliberate reasons. This is about a solenoid, and it's generating some magnetic field, and they want to know how many turns of wire does it have. All right, well, the general equation that we're going to want to work with is that constant for electromagnetism, and then we've got number of turns divided by an L, and then multiplied by the I. Now, this question is asking you to go and find that capital N. But it is capital N that we're finding and not little n. Okay, so just clarifying the difference. Capital N is the number of, they've called it turns. Sometimes you'll hear it called coils. Sometimes you'll hear it called loops. So it's turns. Little n, if we had chosen that equation, that is the number of turns that would show up per meter. And we want to have turns, so we want to go with this equation here. And then that brings up the issue of the L. This L down here is a dimension. This is not the diameter. So back up in the question when they say, oh yeah, I want to tell you the diameter is 0.018 meters, don't pull that into your story at all. We want to go with the 0.3 meters long. That's the value that would have to go in there. I don't even care about what the answer is. I don't even know what it is. You could certainly go and drop in the numbers and find out what that capital N would be. But we're definitely looking for turns and not turns per meter. Okay, this is a little motor, and it's being used to create some torque. It's kind of a simplistic little drawing of the armature there. And that square coil of wire is going to be used to try to hold up that 0.2 kilogram mass. So the 0.2 kilogram mass is definitely pulling down on it, right? There's going to be some kind of mg going on here. This motor is going to have to be doing the opposite of that. It's going to have to create some sort of force up. So the motor's job is to do this. And really what we've got is a section of wire that's in a B field. There's magnetic field just kind of bathing this whole coil in B field. And those wires, they're going to be carrying some current, and it's going to be inside a B field. If you play around with the right-hand rule, doing LIB, with your index finger pointing to the right, towards the south magnet, and realizing that your middle finger, your force finger's got to point up for your right hand, you can actually see that the current in this wire here has got to go that way. That's the direction of the current. And it really is all about an LIB issue. So generically, this is a LIB story, but here's the catch. if you actually go and say, oh, okay, I'm going to say that, the LIB is equal to mg, you're on the right track, but there's one additional little thing we have to throw in there. We have to deal with the number of wires. Every one of the wires here is actually going to help hold this thing up. And you might think, oh yeah, I got to throw a 35 in there. Actually, you have to throw in double that, because the current's going to be going this way over on the other side of the motor, and that creates a nice little downforce over there, and it's like a seesaw. It's actually going to be helping you hold that mass up. So you actually have 70 wires helping to hold this thing up. So you have to throw in a 70 in there to respect that. So the actual calculation would be 70, then multiplied by the length of wire, 0.12, then multiplied by the current, which we're looking for, then multiplied by the magnetic field, decimal 0.050. That has to equal the mg, the 0.2 multiplied by 9.8. Got to be honest, I don't even know what the answer is. Don't really care. I wanted to just talk about how you actually have to throw a 70 in there, because you've got 70 different wires that are helping to hold that mg up. All right. The next page is a little story about some cyclotron motion. It says an electron's going really fast and it crosses a B field, right? So I'm just kind of paraphrasing here. It enters at right angles to a uniform magnetic field. Okay, great. Got a velocity crossing a B field. And it says, yeah, there's a path and it's got a radius of 3.5, 10 to the negative 2. No kidding. It's going to go in a circle. So this is how cyclotrons work. This is what we can call cyclotron motion. And for cyclotron motion, if you take a beginning start of just good old F equals ma, you would have QVB for your force is equal to m times some version of circular acceleration. V squared over r would be great. And if you rearrange that, if you drop a v and move the r, you end up with Q B r is equal to mv. Now your goal in this question, they have said, hey, can you go and find the magnetic field, right? So sure, we're going to go and find this. That means we need to know everything else. We need to know what the R is. Yeah, they gave it to us. We need to know what the V is. Sure, they gave it to us. But then you might be looking at it and going, wait a minute, Q and M, do I have those? And the answer is yeah, but it's hidden here in a word. They said electron. So now you have to go to your formula sheet, because they're not going to drop the numbers in the question. You've got to go to the formula sheet and say, oh, okay, I've got to grab the elementary charge, and I've got to go and grab the mass for an electron. So it's offering it to you, but it's just offering it to you in kind of word format instead of a number. This next one, this one is also talking about the same issue, but it's got a little curveball to it. It says an electron moves in a circular orbit, radius r, in a magnetic field. Okay, top secret. They don't want to tell you what the value is. They've just said, oh, we're going to call it r. The electron moves in a path perpendicular to the magnetic field. Yeah, sure, it's got to do that. Now, here comes the change. Here comes trial 2. If the kinetic energy of the electron is doubled, what's the new radius? Oh, okay, this is checks and arrows. I'm going to, over on the right-hand side of this space here, I'm going to write kind of the main issue. QBR is equal to MV. We're going to be talking about what happens to the R. So I'm just going to rearrange this for R. Some people can do it without rearranging, but maybe it's safer if we rearrange it. So I've got MV all over QB. And this is this principles of physics, checks and arrows as we called it. We're going to redo this trial 2 and see what happens, what changes. Well, the mass won't change. It's the exact same electron that it was before. The Q doesn't change, it's still an electron, and the B doesn't change. Okay, great. Just tell me what happened to the V and I'll tell you what happens to the R, because they're proportional. Oh, they don't tell you what happens to the V. They say the kinetic energy is doubled. Oh, okay, fine. Let's go and use the rest of this space. Let's take a moment aside and we'll go and figure out what's happening to your V. Kinetic energy is 1/2 mv squared. So they're actually going to double the kinetic energy, and it's going to be up to you to figure out what happens to the V. Some people can see it right from there. For others, you might want to rearrange and solve for V. You got to double both sides, divide by m, and then take a square root. So you end up with something that looks kind of like this. 2 times the kinetic energy, all divided by m. Okay, well, your I'm not going to change the 2. It's always been there. You're not changing the mass of the thing, but you do want to take the energy and you want to go up by a factor of 2. Okay, well, if the energy goes up by a factor of 2, that's under a root sign, that means that the velocity is going to go up, but it doesn't double. It only goes up by root 2. It's about 40%. So now I can go back over to the right-hand side of the page and say, hey, I've just figured this out. The velocity grows, but it only grows by a factor of root 2. So the radius is going to go up, but it's only going to go up by a factor of root 2. So I would go with B on this one. It's going to be whatever the old value is, but multiplied by a root 2. Okay, the next one. Looks like it's one of those changing B field stories. And it also, just from here, doesn't look like the area is changing. Okay, a coil of wire, 150 turns, has an area. Oh, that was nice of them. They figured out the area for you. It's placed inside a 1 Tesla magnetic field. Great. The field changes to 0.45 Tesla, so it's reducing. And it does it pretty quick in 0.06 seconds. What's the average voltage created? And which direction does it flow? Okay, so for this picture, again, just one nice little thing that I'm noticing. The B is what's changing, not the A. So because of that, there's definitely a flux change, but it's not about the area. If you're trying to figure out how much that flux changes, that change in flux, when it's time to do the math, it's really going to be change in B multiplied by the area. That's what the change overall is going to look like. So just kind of looking at this, it looks like the change in B is going to be 0.55 Tesla. It's actually dropping by that amount. I'm not too worried about plus or minuses at this point. We're going to sort that out right here. We're going to go and do the direction of the current at this moment. This ring, in the beginning picture, we've got 4 X's. This is, your B1, your external B. Here's your B1 again. It's just changing. There are only 2 X's showing up in the final picture because the B field's dropping. That ring is going to make a voltage, which is going to make a current, which we're going to try to figure out direction for in a second, to make a magnetic field, to try to battle this change. So this ring will actually fabricate magnetic field like this. You can blame that magnetic field that I've just drawn in on the ring. It creates that. So I'm just going to actually leave a little note here. The ring makes this. It's called the induced field. I'm going to call it B2, the second field. So how does it do that? Well, it behaves like an electromagnet. So you grab that ring with your right hand, grab the wires, make that sort of fist around the wires, make sure your fingers penetrate in the center, and what you'll see is your thumb points this way. So during the change, which doesn't last very long, during the change we've actually got a clockwise current. So we can already start to zoom in here on the answer. It's either got to be A or it's got to be C. Now for the actual voltage, the idea here is Faraday's law of induction. EMF is equal to, I'm going to do it. I'm going to deliberately drop that minus sign. We just dealt with the minus sign, so let's keep it out of the math. And then we've got change in flux over change in time. So if you wanted to find that voltage, we can say, yeah, you got 150 turns. Each turn gives you some voltage. And then this fraction, the change in flux there, it's the change in the magnetic field. So it's actually 0.55. That's how much it changed. And then the area, 2 times 10 to the negative 4, and then we'll divide by the time, 0.06. Got to be honest, I don't even know which one it is. I'll let you go and calculate that if you want to. The key issue there is that the current battles the change. It makes a magnetic field, a second one that will try to oppose what you're doing. And you, on this one, don't have to worry about changing the area, so you can actually take the area value and multiply it by the change in B when you do the calculation. 29. This is another one of these motor questions. We did a couple of these on the Chapter 6 review as well. These are great. They're usually pretty simple to do. We can split our page, and on one side of the page over here we can talk about startup, and over on this side of the page we can talk about what happens when you're running. Overall, we're going to be using, just in general, this idea that current It's equal to the source voltage minus the back EMF, all divided by the resistance of the coil. So what do we have? 120 volts and 33 amps at startup, and normal operating speed, current's way down, and you have to find the back EMF. No problem. So I'm going to go to startup first and see if we can get somewhere with this. We've got 33 amps, 120 volts for the source. There's no back EMF. It's like subtract 0, right, or just ignore it. And then there's the resistance of the coil. And when you do this, you find that the resistance of the coil is 3.63 ohms. You can take that information about the resistance of the coil, and you can take the information about the source voltage being 120 volts, and you can take those two things across over to this side of the page. Those things don't change when we go to do the next calculation. At full speed, we're at 2.7 amps. That's 120 minus your back EMF generated by the coil, all divided by that very same resistance, 3.63. 2.7 multiplied by 3.63 is around 9.8, I think, somewhere in there. So that's 120 minus the back EMF. Don't take the 9.8 answer. The 9.8 is the value for the numerator. It's the effective voltage. But actually, we want to take the 110 answer. You need to reduce that 120 by 110 to get it down to around 9.8 or down to around 10 volts. All right, moving along. For 28, it's on our last page of this here, we've got a story about a bar magnet moving towards the solenoid, and you're going to try to figure out which way the current flows through this thing called a galvanometer. It's a very sensitive ammeter, and which way is a magnetic field going. But we should be careful and read which V field that's actually talking about. So, bar magnet's moving in. What is the direction of the current through that meter? And what is the direction of the magnetic field? Here comes the really important information. Produced by the current. Okay, so that's the second magnetic field. I've always suggested that you draw before and after pictures. I'm going to do that here, and I'm going to be a little bit cheap about how I do it. I'm going to put my before picture over on this far left side of the page. So here's the before picture. The magnet's out here. Got the north end. Got the south end, and it's really, really, really far away from the coil. So sure, there's a magnetic field going into the south end, but look, it's not going anywhere near that coil over in the middle of the page. Then later on, here's my after picture. It's the one they gave me. I've got that coil now very close to the coil, and it's moving in even closer as time goes by. So this blue B that I'm drawing, that's the first magnetic field. It's the one caused by the magnet. And now in the after picture, that first magnetic field is going to start to go in through that coil. This is still B1. And I guess it comes out of the north end like that. So that coil goes from having no magnetic field going through it to having some flux going off to your left. And what we need to do is think about how this coil is going to react. We're going to go back to a situation where we have no flux. So it's going to generate a voltage to make a current, to make a magnetic field that opposes this new magnetic field that's off to the left. So that coil will now make a magnetic field going this way. There's your induced field. So it's really important that we look and see which field they're talking about. And this thing says, hey, the magnetic field produced by the current. So that B2 they're talking about. And it looks to me like B2 is off towards the right. So how does it do it? Well, it creates a voltage to make a current. I'm going to imagine grabbing one of these wires, maybe this wire right there. I'm going to imagine grabbing that wire with my hand, just doing a fist grab, making sure that my fingers point in that green arrow direction. So right underneath that purple wire, your fingers have to point off to the right. And to do that, you have to have your thumb pointing down. So you've actually got currents going this way, kind of heading down on the top. So that makes the current come down along here in that direction. So it looks like in the very sensitive ammeter there, that galvanometer, it looks like it's going from X to Y. So yeah, it's got to be answer A for this one. Final example. This is actually a question that talks about the demonstration we did in class where you drop a magnet into a pipe. In class we did a copper pipe. This one's aluminum. And the magnet falls very, very slowly because it turns out the pipe actually generates some currents, one above and one below the magnet. And they're asking you, well, which way do these circular currents in the pipe go? Do they go in the 1 or the 2 direction above the magnet, or the 3 or the 4 direction below? This is kind of 2 questions in one, and for each question you need to do a before and after picture. So it's going to be a little busy here, but I think we can get most of it done over here on the right hand side of the page. I've got my before picture, and I've got my after picture just to the right of it. And what I want to do is I want to imagine that that pipe of aluminum is actually made up of a whole bunch of little rings. It's like a stack of A and W onion rings all on top of each other. And there's one ring here, and there's another ring down there. And we're going to take a look at this entire stack of rings and just focus on those 2 rings. And I want to try to draw before and after pictures, so I'm going to draw it like this. I'm going to say, okay, here's the ring that's up near 1, 2. Right, it looks like this. And there's the exact same ring afterwards. And let's go way down the page here. Let's go down to about here and say here is the 3, 4 ring. So this magnet's falling. In the beginning part of the story, the magnet is up here. But then later on, it falls until it's down here. And they've got the north end at the bottom. Okay, fine. And now, permanent magnets. Well, they have their own magnetic field. So I'm going to draw that in, and I'm going to call it B1. Magnetic field goes into the south end. So this ring is going to have magnetic field flexing down towards that magnet this way. But then, the north end, its magnetic field's missing the lower ring, hasn't got there yet. So there's B1. Later on in the day, this magnet has fallen. It's now so far down that the magnetic field going into the south end is missing the upper ring. But the lower end does have a magnetic field going down into that lower ring. Okay. That ring, or that set of rings, is going to respond. They're going to generate voltages to generate currents to try to stop you from making those changes. So in the after picture, that 1, 2 ring is for sure going to generate its own magnetic field that goes this way, trying to replace what you took away. The lower ring is actually going to create a voltage to create a current to create a magnetic field that goes this way. So now you just have to do fist grabs for each of those rings. Let's do the top ring here. Maybe imagine grabbing that ring with your right hand. Grab it right here, and make sure that on the center of it, your fingers go down in. And what you'll find is your thumb, if you're using your right hand, your thumb has to go this way. So it's in the 1 direction. For the lower ring, maybe grab it right on the front part of the ring. Grab it right here. And if you grab it there with your fingers pointing up to make B2, you'll see that the current has to go in the 4 direction. So it's the 1, 4 answer. It's actually B. By the way, a little bit of trivia. This is just some extra little information here for you. If you think about this coil of wire being like a very, very simple electromagnet, I'm just going to cover this up and think of it now as being like an electromagnet. That electromagnet, it's a very simple electromagnet with 1 turn, has magnetic field coming out of its bottom end. That makes this bottom end a north end. And now think about what the north end of this electromagnet is going to do with the south end of this bar magnet they're going to attract. So it tries to hold it up. Doing the same thing down here with this lower ring, it's like an electromagnet. And look at the green. The green is coming out of the top. So this must be the north end of an electromagnet. And a north here are going to repel. So the lower ring is becoming an electromagnet trying to repel the falling magnet. The upper ring is becoming an electromagnet trying to hang on to the falling magnet, and that's why the magnet falls so slowly. And that's the end of our Chapter 7 tutorial.